Hi everybody, my name is Arno Kolster, and most of you know me, but I started a small consulting company with my colleague Ryan Quick a couple of years ago. We came from the PayPal side. No, they're not. Well, this one might be. But just shameless marketing for about 4 seconds. We do a lot of different things on the technology consulting side. We sort of do the gaps between cloud, HPC, and enterprise. And I'm one of the very few people that come from an industry side of things that have sort of moved into HPC over the last decade or so. The title of my slide is Obscured by Clouds. It's not really about cloud, it's not really about HPC. We're going to be talking about integration of HPC systems. And for those of you, well, it looks like the age of the audience is about right to remember Obscured by Clouds by Pink Floyd in the early 70s. This is where the album cover comes from. So, great. All right, so I do have to talk a little bit about why I'm actually here. 7 years ago, I did my first presentation in front of most of this group. And I talked about PayPal's SGI system to do fraud detection at scale. So we were doing millions of events a second across 192 cores. And the reason I'm explaining that is a few years later we talked about systems intelligence, again about streaming analytics and using anomaly detection to look for anomalies in the system to monitor for operations to tell the operators there's something wrong. So why are we here? Why am I here again talking about this? Well, it's time that we explain everything that we've been talking to this audience about for the last 7 years, which is essentially that enterprise and hyperscale architectures are slowly merging into HPC. We talked to Steve at ISC. He said, the work we've been doing in the last couple of years is really awesome. You should explain it to the HPC User Forum. So basically, cloud is a reality. We heard Steve Scott talk about it this morning with Shasta, that they're starting to embrace some of the cloud technologies that are there. There's a huge fear of missing out on latest technologies. You hear about Kubernetes, you hear about Docker. All these things are slowly starting to get into the HPC world. And you've also got the cloud providers, all the major ones now, providing HPC in the cloud. So a majority of our work has been leveraging hyperscale and merging some of the hyperscale architectures and technologies into the HPC space. And basically it's time for us to tell you that we've been eating our own dog food and leveraging everything that we've been talking about in some of the work that we've been doing. But there's still a huge learning curve on the HPC side. And we've been helping a lot of our clients in sort of leaping into understanding what those technologies can do for you. And the other problem we've got is the enterprise folks are still having struggles with HPC technology. For instance, Ryan, my colleague, just installed 96 GPUs last week with 8 FPGAs for a client. It's a complete enterprise client. We're not quite sure what they're going to do with those yet, but we've deployed them, so they'll probably be calling us back, asking us to help them understand what it is that they built. So we're going to talk about 2 use cases. The first use case is a system that's very near and dear to most of you. This is Summit. And we were brought in to help do some, let's say, high volume data analysis and build an infrastructure for Summit that was able to do monitoring of all the metrics coming off the nodes. So I met Jim Rogers, who is one of the directors for facilities at Oak Ridge, about 6 years ago. And I have to thank Susie Titchener for introducing us, because Susie was paramount in getting PayPal at the time to talk to Oak Ridge about the Industrial Partnership Program. So Susie basically introduced us to Jim and a few of the other leaders at Oak Ridge, and it ended up with a partnership with PayPal in developing some software between the two parties. I did a talk at Cray User Group 2 years ago in Redmond, and Jim was in the audience, and I was talking about streaming analytics. And at the end of the talk, Jim pulled me aside. He said, hey, can you help us do streaming analytics on Summit? Because I've got a problem. I've got 4,600 nodes, all streaming data off them, and I have no idea what to do with them. And I said, yeah, we can help you with that. So our engagement with Summit started with Oak Ridge a year ago. And what we've been doing with them is essentially delivering an infrastructure that Summit can use now, that Oak Ridge can use now, that pulls all the metrics off the nodes, analyzes them real time, and present information to the operational folks, as well as the data scientists and the developers as to what exactly is happening on that system. So everyone knows Summit is the largest supercomputer in the world right now, water-cooled. There's 4,600 nodes, and there's no mechanism in place at the time for Jim and his team of folks to understand how to cool that computer system down and actually understand exactly what's happening on a per second basis. And his real goal here was to save energy and to save money, which is a good goal for everybody. He wanted to be able to understand the temperature of the water at any time and then use historical data sets to predict what jobs are coming and how to basically keep the water temperature as even as possible so that he didn't have to turn on the cooling systems. Because as soon as you turn on those cooling towers, the increase of energy goes up and he has to start spending money, which is not what he wanted to do. One of the challenges in Summit is it's such a large system that by the time Jim turns on some water, cooler water at one end, it takes about 3 minutes for that cooler water to propagate across the system. And of course, it raises the temperature. So we decided that we'd build some systems intelligence into the whole system for him to understand how he can change the temperature, if at all, and move things along. All right, so we had some design goals. When we stepped in and worked with the Oak Ridge team, we had some design goals in place. We wanted to build telemetry inline, so it's basically the data comes off the Summit nodes and it gets streamed onto a pipeline, and we basically start reading that information. We persist it so that data scientists can look at it later, but we're really interested in what's happening in real time. We wanted to enable some cloud-style messaging, and I'm not going to talk too much about the cloud per se, but a lot of the techniques and software that we used is being used in the cloud today. So there's a sort of a hybrid mixture between what we built for Summit and what can be used in the cloud. Huge scales of data, right? They can add more and more data without having to increase the resources to consume them, which is really good. And from our days at Hyperscale, PayPal for instance, a single point of failure cannot result in another failure. So everything is built in triplets, so that if you have a single point of failure, your system will keep running. So those were some of the design goals we went for. At the time, we had 4 different source metrics. We had OpenBMC from IBM, which is the framework that's pushing metrics out from each core, or each node I should say, at the rate of about 100 a second. So these include all the temperatures for the GPUs, all the temperatures for the CPUs, temperatures for the DIMMs, temperature for the HBMs, etc. There's also power metrics there. So each node is pushing 99 metrics a second, so that gives you 456,192. We also took data from the IBM job scheduler, LSF, and that's coming out at the rate of about 10 seconds. Because there's constantly scheduling jobs across the cluster, so we're consuming both the metrics off the nodes as well as the job metrics. We also grabbed data from NOAA, and the reason for that is Jim wanted to understand what's happening on the weather side, so he could see if tomorrow the day is going to be warmer or cooler. He could schedule the chillers to go up or down. And then last, we intended to push information back to the PLCs that were controlling the water towers, so that we have intelligence and a constant flow of being able to take what the intelligence of the system is doing and then writing code back to the PLCs to say, okay, bring up or down those water chillers over time. We also added metrics from the development platform, which is called Ascent. That's where we developed against. We developed against Ascent and then pushed the container versions of what we did to Summit. So we basically added a lot of metrics, logging and collations, etc., to the system, and that gives us about 460,000 metrics a second coming off that pipe. Now, it might seem like a lot to you, but remember, when I first talked to you about 7 years ago, we were doing about 7 million events a second on PayPal. So we're quite used to and quite familiar with doing large-scale systems. But what does this allow these guys to do? With 460,000 metrics a second, it's pretty spectacular. So what did we build? And I'm going to quickly go through this, but we started with the most important part of the infrastructure, which is the message bus. We talked to Oak Ridge and the developer and said, what would you like to use as a message bus? Because we're agnostic, we don't really care. He said, we want to use Kafka. As we said, that's great, we'll use Kafka. He could have used Rabbit, he could have used AMQP, he could have used any of the others, but Oak Ridge was familiar with Kafka, so we decided to stay with Kafka. So we've got the data sources here that I mentioned, OpenBMC, the LSF job data, NOAA weather data, the PLC data, and then any other data they want to add now or in the future, they can just push it to the bus. The NOAA data is being pulled at the rate of about once an hour, only because NOAA doesn't provide any information faster than an hour, so we pull it every hour. So from there, we persist it to some degree. We used Prometheus as a time series database, which essentially takes every second and creates a time series out of it. We used etcd and consensus configs to make sure that all the nodes were in sync. We used Elasticsearch for log metrics and log understanding. And then we also had structured relational databases to keep track of various items in the nodes. Now, any of these can be added to or subtracted to because the message bus is ubiquitous. You can just subscribe to the bus with the topics you're interested in and grab that data. From there, of course, you want to learn everything you can. We've talked about machine learning and we've talked about neural networks. All this data is being pushed on the bus. It can be pulled off. And then the data scientists can go crazy with this new data sets that they have. So we're basically doing streaming analytics, and in the end, it's going to go to do PLC recommendations for turning up or down the water chillers, and we're going to use monitoring, reporting, research for the data scientists with what data is coming off those nodes for the jobs they run. Oops. And a lot of reporting. So here's some of the technologies that we brought in and used at Oak Ridge. Somebody mentioned earlier, or asked earlier of Doug about Kubernetes and Docker. We brought Kubernetes and Docker in that are being used at Oak Ridge. Everything's microservices, which is essentially another cloud technique that we're using. Kafka I mentioned before. We've got Docker containers that are basically contain the little microservices. We're using OpenShift and Kubernetes for orchestration of all these little services. Spark streaming for analytics across that bus. Prometheus, I mentioned already, is a time series database. Jupyter, which is like a Python workflow, which the data scientists really like because Python 4 is around the corner, like Rick mentioned this morning. And then we use Grafana, which is a very common monitoring tool for monitoring, and Seaborn for visualization. So there's a whole bunch of new technologies that we brought into play. All of these are very, very common in the open source world, and I think a lot of young people like to play with this stuff, so it's a way of getting some of the younger people involved in HPC. So some of the breakthroughs that we brought into play, it's a new paradigm. There's no more looking at databases for data. There's no more waiting till tomorrow to look at the data. It's basically real-time data. What you see right now is what's happening right now. It's also agnostic. We can put it in any format you want on that wire and then pull it off and reformat it any way you like. So the other cool thing, and I'll show you, is overlapping data sets give you more insight into what's happening. So what can be done now? Okay, we're capturing 99 metrics a node. We can capture all the data for the different power consumptions of each of the components. We can visualize per second what's happening. We can actually understand the complete picture of what's happening on Summit, as well as at a node level, which they could never see before. We're able to optimize the system for energy efficiency. So temperature-wise, job-wise, Jim and his team have a great way of turning knobs up or down depending on what's happening. And we can also keep adding more and more data to this infrastructure because we built it so that we could do that. The impact is huge, all right? We can now micromanage a huge system. So the largest supercomputer in the world is now being micromanaged by microservices, a cloud thing. We have the ability to do predictive analytics, not only on the job scheduling, but also on what's happening on the temperature and energy levels. And it's possible to actually understand what Summit is up to at any point in time. So I'm going to show you a few slides. So this is a this is actually Grafana. This was put up in Jim's office, if you will, and he was so excited about it he would never take it down. He keeps looking at it. When we were there a few times, he kept looking at it. But this is sort of a way of being able to monitor the system in real time that they never had before. And in this case, Grafana is very custom driven. You can essentially choose any of the metrics you like and graph them anyhow you like. It can also alert you on different things. So if the temperature goes up more than a degree, you can actually get alerted. If you want to see this up closer, I'll show it on my laptop. But the really cool thing is this particular slide, the next two slides. And unfortunately, if I knew there's going to be 3 slides here, I would have 3. I would have 99 for all 99 metrics. But what I'm going to show you here is this is a layout of Summit. It's all 4,600 nodes across 8 rows. And the white areas are basically InfiniBand nodes and network nodes. But the other ones are all the single nodes. And what you see here is power per jobs per second. Now, normally it would just be power. So each of the squares would be power. But we can now actually add jobs and show you which jobs are the ones that are increasing the power on this. And this is basically a movie we captured because it's easier to capture a movie with all the data coming in. And you have to imagine that there's actually 99 of these things for each node. So at the same time that you're seeing this, you have to imagine another 450 things playing at the same time. Or actually, it's 4,000 things playing at the same time. But I'm going to play it, and if you watch closely, the jobs change. Here, let's see this. The jobs will change here, and then the little white dots will change here. So I'm going to play this one, and we'll see how it goes. But this was happening in real time, and you'll see jobs moving in and out of the system, increasing and decreasing the power on each of the nodes. And so this is like a very simple visualization. You can get really, really fancy with some of the software, but I think Oak Ridge plans to have their visualization experts do this in a much better format. But this is just something that we wanted to show. And then this is the temperature per jobs per second. It's the same thing. When a job comes on, you'll notice the temperature of the nodes pop up a little higher than normal. So this was just by visualization, you can see how active the system is at any one time. When we saw this, it was pretty exciting. So. All right, so I must say that even though it looks great at the end, it wasn't without challenges. Mostly around, the first thing was it took a while to get all the legalities and the statement of work fixed. We had some resource constraints on scheduling. Summit was not quite ready yet, and we were working on the development side, and we had some challenges on the technical side, but we got it to work. We had to work within the confines of the security model that they have, which really helped because we basically containerized everything, and so we would work on the development platform, containerize it, and then push it to Summit itself. And we had limited hardware to work with. So everything that you see there, we basically built on 3 small nodes. And again, that's basically coming from a cloud microservices architecture where you can actually build things really, really small and scale them out as you will. So the effort was worth it. I'm starting to run out of time, which is funny, but I'll let you read through this. What I really want to focus on is on the Exascale side of things. I know I've seen a few slides today and about the ECP projects, but I don't see any slides about monitoring or how to consume all that data from all those nodes. It's really important from both an energy perspective as well as the data scientists to understand how they can actually use that data to make their jobs more efficient. Why is my job spending more time on the CPU than on the GPU? Why does my job consume more power than someone else's job? These are really important to make these large-scale supercomputers more efficient. And if you have the system in place, the platform in place to be able to do that, it really makes things a lot better. So there's myself and my colleague Ryan and our good friend Merle Giles, who is our business development partner in front of Summit. Use case number 2, I'm going to really go through this quickly. This is an aerospace defense contractor. This is a picture of Argonne. I'm not sure what happened to that other side, but it should have been a circle. But anyways, they probably didn't have the satellite imagery. What I want to talk about here is the client had a problem, and they're wanting to move HPC workloads into the cloud, and they didn't really know how to do that. So they asked us to step in and help them figure something out. So essentially, we said, okay, we'll give you a 2-day training course, but they had minimal cloud experience. They wanted hands-on training. They just didn't know all the literature or language about cloud. So we came in and we did a 2-day Cloud 101 course with them, and we're having weekly conversations with them, which is really great. But the key is that we wanted them to think about how to break up their monolithic HPC jobs into microservices. And that's the first step into sort of bridging the gap between HPC and cloud services. You need to break up those big tasks into little ones to make them much simpler. So we said, okay, give us the project that you're working on and we'll go through it together. So this is their proposed architecture. I've sort of dimmed out some of the boxes so you don't know who they are because they want to remain anonymous. But you can see the complexity here. They're trying to do a hybrid model both on-prem and on cloud. And we said, okay, well, this is never going to work because it's just way too complex. So I mentioned complex. It's extremely difficult to scale. It's hard to add new components and new features to that model. They're using a mix of legacy systems, Windows, Linux. It's a kind of a mess. So we came up with something completely different. Each of these little green boxes is a microservice. Very small little program that does maybe one thing within 10 lines of code. So we broke up their whole model and basically came up with our own little model that worked. So we've got these little microservices working, and then here you see the message broker, which is really key again in this architecture. This is a diagram of availability zones. It could be Google, it could be AWS, but essentially we've got what the previous diagram once, and then I've tripled it here. So there's an availability zone in the yellow, and there's an availability zone at the bottom, meaning that there's high availability everywhere in the cloud. Here you see the message broker. That's essentially talking between the availability zone and a site where they're interested in talking to the cloud from. And those are basically the 3 sites that they're interested in. You can keep adding sites and using the message brokers as passing data around. So we've done a cloud-centric model here. They've got availability. It's simplified. They can basically expand as they will and add more things to it. So in summary, I'm going to finish right on time. We've been using cloud architectures and cloud techniques to maximize the performance and scalability of some of the use cases I presented. Middleware, that is the messaging layer, is extremely important. In the Oak Ridge case, we used it to basically gather the data from the nodes and push it out. In the second use case, we've basically used the messaging system as a go-between between the sites and the cloud availability zones. So they can just use that as a bridge, if you will. Breaking large tasks into smaller ones, microservices, and leveraging some of the new software stacks that are out there makes sense. And then, of course, microservices can be scaled as many as you want. If you need more image analysis microservices, you just spin more up using Kubernetes. You could create thousands of them. And so it makes perfect sense to do and break tasks up into smaller units. So I finished with 2 seconds to go. Again, Pink Floyd covered, but thank you very much for listening, and hopefully that give you some insights into what we do as well as some cloud techniques to use in HPC.
Questions for Arno?
Deborah.
Pink Floyd fan. Awesome.
Yes, I saw those 2 little furry things here, and I thought about that
Animals.
song.
Oh, yeah.
All furry species, whatever it is.
Question. So, love the talk. If you add edge and fog and really extreme conditions, does it break the model?
No.
Or is it extensible?
No, it doesn't break the model. Only because it depends where you want to do your analytics.
Suppose you're doing it on a drilling platform, right, out at sea.
It's perfect. Because you've got all the metrics from the drilling platform there, and you either aggregate and analyze there, you analyze there and aggregate and push what you really need back to the mothership, or you just do everything there.
Hey Arno, great talk. Just one general question. Is the model general enough to be applicable to any other system that you apply to Summit?
We could probably take the container and push it to you guys, or Lanel or Argonne. It's basically containerized right now. We could just... Thank you very much.
Thank you, Arno.
Thanks.